The Nyquist stability criterion is a graphical test to determine the stability of a closed-loop system based on its open-loop frequency response. Remember that by open-loop frequency response, I mean L of j omega, that is, the multiplication of the frequency responses of all the elements throughout the loop. In this case, L of s is equal to C of s, P of s, H of s, so the criterion will tell us whether this loop has unstable poles just by looking at C of j omega, P of j omega, H of j omega. You may ask, what's the point in doing that? In the end, the closed-loop poles are the zeros of the characteristic equation 1 plus L of s is equal to 0, so I can always calculate them to see if all of them are in the left half plane. Well, that's true, but you must realize that in many occasions the control design process is carried out by properly shaping the open-loop frequency response. So it's very useful to know at any point during that process whether the closed-loop system is stable, without the need to compute the exact closed-loop pole positions after each and every modification we make on the controller. Moreover, on some occasions we have the frequency response of the plant obtained by experimentation, but we don't have its transfer function. In those cases, the Nyquist criterion comes in handy, because it allows us to use directly the result of our experiments. Finally, with the Nyquist criterion, not only do we know whether the system is stable, but we also get an estimation of how far our system is from stability or instability. To derive the criterion, we need a little bit of complex variable calculus. In particular, we have to resort to the Cauchy's argument principle. If you compare real functions with complex functions, you'll notice an important difference. Real functions assign a real number to each value of the real axis, thus defining a curve. Complex functions assign a complex number to each position of the complex plane. Each position in the S-plane leads to another position in the f of S-plane. If instead of discrete points we take a trajectory, the function yields an image trajectory. What is interesting here is that the particular shape of the image trajectory depends both on the function f of s and on the trajectory that has been passed to the function. And a key feature of this dependence is described by the Cauchy's argument principle. The principle shows that if a closed trajectory, which we'll denote as capital gamma s, is passed to the function f of s, and such function has a zero inside the area encompassed by the trajectory, then the image trajectory, denoted as capital gamma f of s, will encircle the origin in the same direction as gamma s. We say then that there has been a positive encirclement of the origin. Similarly, if what the input trajectory encompasses is a pole of f of s, then the image trajectory will also encircle the origin, but this time in the opposite direction. In this case, we talk about a negative encirclement. In general, the following relation is true. If we take a closed trajectory gamma s with certain direction and pass it to the function f of s, generating an image trajectory gamma f of s, the net number n of encirclements of the origin by the image trajectory is equal to z, the number of zeros of f of s encompassed by gamma s, minus p, the number of poles of f of s encompassed by gamma s. So for example, if gamma s is a closed trajectory with clockwise direction which has within its boundaries 3 poles and 1 zero of f of s, then gamma f of s encircles the origin twice in counterclockwise direction, because n is equal to 1 minus 3 minus 2. How can we benefit from this? Well, imagine that we pick for f of s 1 plus L of s, the characteristic equation of our closed-loop system, and that we also choose as the input trajectory one that encompasses the whole right half plane in clockwise direction. In that case, the argument principle is telling us the number of net clockwise encirclements of the origin by the image trajectory gamma 1 plus L of s is equal to the number of zeros of 1 plus L of s in the right half plane minus the number of poles of 1 plus L of s in the right half plane. But notice this, the zeros of 1 plus L of s are the roots of the characteristic equation, or in other words, the closed loop poles. So in this scenario, Z is the number of unstable closed loop poles. This is what we're looking for. On the other hand, 1 plus L of s can be written as 1 plus the numerator of L of s over the denominator of L of s, which is equal to the denominator plus the numerator over the denominator. So as you see, the poles of 1 plus L of s are no other than the poles of L of s. Therefore, in this scenario, P is the number of unstable open loop poles, which is known. So in order to find Z, the number of unstable closed loop poles, all we need to do is to define a trajectory encompassing the whole right half plane. Pass that trajectory to the function 1 plus L of s and count how many times the image trajectory encircles the origin. Such a trajectory was defined by Harry Nyquist, and it is known now as the Nyquist contour. The Nyquist contour consists of 3 paths. The first one starts at the origin and goes up all the way to 0 plus j infinity. The second one is a semicircular arc with infinite radius that moves clockwise all the way down to 0 minus j infinity. Finally, the third path connects 0 minus j infinity with the origin, thus closing the contour. Now we have to find the images of the contour, which isn't as difficult as it may seem. Let's see, the images of the first part of the contour are given by 1 plus L of j omega, with omega belonging to the interval 0 infinity. This is just 1 plus the open loop frequency response, which we have assumed to know, so we can draw it in the plane. Now, if L of s is a proper function, meaning that the degree of its numerator doesn't exceed the degree of its denominator, then 1 plus L of j infinity is a real number. In fact, if it is a strictly proper transfer function, that is, if it has more poles than zeros, that real number is 1, because L of j infinity goes to 0. In either case, you can easily check that that point is also the image of all the other points along the semicircle. In other words, the whole image of the second path is just one point in the real axis, and in most cases that point is -1, 0. Finally, the image of the third path is given by 1 plus L of j omega, with omega belonging to -infinity, 0. Obviously, these are the complex conjugates of the images of the first path, which means that the image of this path is symmetric to the image of the first path, with the real axis as the axis of symmetry. In conclusion, in order to have the image of the Nyquist contour, it suffices to take the open loop frequency response, add 1 unit to it, and draw the result as well as its reflection on the real axis. Now we can count the number of encirclements of the origin. According to the previous results, that number is going to be equal to the number of closed loop poles in the right half plane minus the number of open loop poles in the right half plane. The finishing touch and the criterion comes by realizing that if 1 plus L of j omega encircles the origin, then L of j omega encircles the point -1, 0. Therefore, we can work directly with the open loop frequency response, counting its encirclements of the point -1, 0, which from now on will be called critical point. So to make a long story short, the criterion can be stated as the net number of encirclements of the critical point by L of j omega, with omega between -infinity and infinity, is equal to the number of closed loop poles in the right half plane minus the number of open loop poles in the right half plane. Recall that the unknown in this equation is Z, the number of unstable closed loop poles. Remember also that our purpose is to keep that number equal to 0 throughout the design process, in which we will be shaping L of j omega. As a consequence, we must always ensure 2 things. First, there are no net positive encirclements of the critical point. If there are any, then n is greater than 0, and since p cannot be lower than 0, then z is greater than 0, which means that the closed loop system is unstable. And second, there are as many counterclockwise encirclements of the critical point as right half-plane poles in L of S. In other words, n must be equal to minus p. In particular, when the system is open-loop stable, there shouldn't be any encirclements at all.